Hello all, welcome to a fresh new lecture on the topic short-term Fourier transform. This is Dr. Anirban Dasgupta and let's get started. So, we have analyzed the signal in the frequency domain using discrete Fourier transform, and using DFT lot of problems can be solved, even practical problems. But there are some issues with the discrete Fourier transform, and what are them? So, let us study these one by one. So, first is boundary effects or edge artifacts. So, the limitation is that, so when a finite duration signal is used in the DFT, we assume that the signal is periodic. Why? Because we are getting line spectra, and line spectra we know will occur for periodic sequences. So, DFT assumes that your x of n is a periodic extension. This is the discrete Fourier series of the periodic extension of your signal. So, say if this is my signal, say let us say I have 8 points. Now, what will happen is, let me use a different color, and this will be repeated. So, this comes here. Similarly, here this tall value will come, and it is assumed that this is going up to infinity in both directions. So, this sudden change, these are called the boundary effects, and this will introduce additional frequency which are inherently not present. This will be probably clear if, say, this sample had a smaller value, then you can acknowledge the boundary effect nicely. Say this value is small. So, now you see this sudden change is creating a artificial high frequency which is not at all there in the signal, or if this value is a negative. Same thing will happen if I do change this value, because it is a periodic extension. So, if this value is very small like this, so this is an artificially induced high frequency component. So, this is taken care of by transforms like the discrete cosine transform and the discrete sine transform. So, what discrete cosine transform will do? So, if this is your signal, it will do an even extension of this signal and then assume that even extension is periodic. So, if this is my signal, and so if this is my index 0, if I do an even extension, again let me use another color. If I do an even extension, now see this is quite smooth, and even here also, since this is an even extension, I will get this repeated or this very smooth. So, this is a smoother version. This is what DCT does. So, DST will do an odd extension. Now, you can keep this in mind that we studied odd and even signals. So, this is one application to understand the properties of discrete cosine transform and your discrete sine transforms. Another is real and complex signals. So, even though we have a real signal, very nice looking practical signal, if we do the DFT, it will produce lot of complex things. Now, I agree that this is to encapsulate the phase things, but this is not a real valued transform, and it is difficult to not only store, but it becomes very complex to analyze with imaginary values. So, this is again solved by DCTs and DSTs, which are real valued transforms, and this is more efficient for real valued signals, and in this manner it will improve the computational efficiency. How? Now, if I have two complex numbers, then I need to do multiplication of the reals, multiplication of the imaginaries, and then cross multiplication of real and imaginary. But if everything is real, the number of multiplications and additions will get reduced. Also, this is efficient to store. because if I have 8-bit memory and if it is a real 8-bit signal, so one memory unit will be sufficient. But if it is a complex signal, then I need a paired storage unit for storing the real and the complex values. Then signal compression and reconstruction. So, we also see that the DFT is not very good at compression and reconstruction, because there will be a large space in the frequency. What do I mean? So, compression means, so if I have a sine wave of a single frequency, that is easy to store. If I just know the frequency, I will store that. But in real world, my signal will be composed of lot of sines, and probably you will get to store all the components, which is not memory efficient in compression. But DCT coefficients will be compact, so that you do not need to store all the n values. You may be needing to store only those values which are high enough and truncate low order DCT values. And this is commonly used in our image compression, that is JPEG. Of course, this is one of the most popular image format which all of you have been using, the JPEG or JPG image format, and the MP3 audios are so popular. So, this MP3 and this JPEG, they use compression which is based on the discrete cosine transform. Another problem is lack of time localization. So, as I showed in the introduction to time frequency analysis, that suppose I have a slow varying wave of say 10 hertz and suddenly I have a fast wave and then it goes slow. So, I know that both slow frequency and high frequencies are present. So, this is 10, this is 30, this is comprising the 30. So, I know which components are present in the frequency domain, but where they are present I do not know. Also say I am singing. So, while I am singing, both vocals and instruments are present, but then there will be some prelude or interlude in my song where there are only instruments. So, I know that what frequencies are present, but where they are present in time it is difficult to localize by just looking at the spectra. So, this is solved by something called short term Fourier transform, which is the topic of discussion in this lecture. So, what short term Fourier transform does is, instead of looking at the whole spectra, we will be interested to looking at small sized windows and evaluate the spectra of that window. Then handling non-stationary signals. So, what is non-stationarity? The signal properties will vary. Like I gave the example of the chirp signal where the frequency is increasing linearly with time. So, real world signals are often non-stationary in nature. So, just looking at the holistic spectra will not give a good analysis. So, the FFT or the DFT will give the snapshot of the entire signal's frequency content. So, we should be looking at small overlapping window which is solved by our short term Fourier transform, and then we can select different types of windows to control something which is called frequency leakage or spectral leakage. So, this is what the short term Fourier transform does. So, here say we have this signal, and now if I do the DFT of the whole signal, say this is of length 100. So, I will get the frequency content of the total signal, but I do not want that. There are some events like this and this where there are a lot of variations, I need to capture that. So, what I will do is, let us select a window which is of size 20. So, typically I will have 5 windows which are non-overlapping. Of course, we can also use overlapping windows. So, if I select this first window which is, if this signal is x of n, then I would say this sub window or sub signal is x of 0 to x of 19, and I will compute the DFT and have a spectra for this. So, this is a vector, the DFT magnitude spectra will be another vector. Next, I will move this window from index 20 to index 39, and next I will do for 40 to x of 59, and similarly we will go on to other non-overlapping windows. So, this is the mathematical representation for STFT of a signal x of n for a window which is given by w of n minus t. Now, t is the translation of this window, and this is the index which represents the position of window in the time domain. And this window you can select anything. So, the window, if you just take the samples directly, it is called a rectangular window. But the problem with rectangular window is that there will be sudden changes in the signal values from a finite value to a sudden 0 value. So, rectangular window is easier to like use but or understand, but it will cause lot of spectral leakage. So, there are other windows like Hamming window, Hanning window, Bartlett window, Gaussian window, lot of windows are there. So, the window function in this case is typically moved across, and in the short term Fourier transform this length is fixed and the frequency resolution is depending on the length of the window, and that is for any DFT algorithm. So, when we do an endpoint DFT, if my n is large, my frequency resolution will be high and vice versa. So, if we have a larger window, we will have a better frequency resolution. Like as I said that if I see a long part of the signal in time domain, I can exactly know that, not exactly, but I can better know that what frequency content is present. But if I reduce the window size, say I have just 2 samples, with the 2 samples what frequency information will I know of the signal? Kind of nothing. So, more I am localized in time, I am more uncertain about what frequencies are present, but more I am localized in frequency, that exactly this is present, that exactly 50 hertz is present, that requires me to have infinite length window in time. So, this trade off has to be managed depending on the problem. Like if we are localizing an event, then we have to know that what should be a typical duration of that event. Like in a seismic signal, we are localizing some event like earthquake kind of a thing or some vibration of the ground. So, in that case we should know that what is the existence of that high frequency component in the signal, so that I can select my window length in the STFT. And the resultant plot is called the TFR or time frequency representation, where the x axis represents time and the y will represent the frequency. So, this is the mathematical definition, where here I have selected the window as a discrete index m. Now, let us take an example of computing the STFT. So, here I have sum of 2 sinusoids of frequencies f0 and f1, and for simplicity let us say I take f0 as 5 hertz and f1 as 10 hertz, and we will use a sampling rate of 100. So, this will be so 2 pi f0 n. So, if this is already in n, there is no problem, but if this was in t, so you have to do this n by fs. So, first thing is you have to select your n, and then I will divide the signal into this, say I can select overlapping segments, say I can take 25% overlap, I can take 50% overlap. So, this also needs to be taken care of, because more overlap you take, more number of computations you have to do, but you get a better localization in time and vice versa. Then I have selected some segments, so I have to do the Fourier transform for each segment. That is, first I will take one window, do the Fourier transform, then slide the window, then do the Fourier transform, again slide the window, do the Fourier transform. And typically these sub signals or overlapping segments or even non-overlapping segments can be computed in parallel, because these transforms are independent of each other. So, if you have the computation facility, then you can do them in parallel. So, in that manner also you can do faster processing. You need not wait for the completion of the previous stage. And then finally, we will plot this in something which is called a spectrogram. So, here we can clearly see that this yellow color is representing the highest magnitude, and we can see that in this region 10 and in this regions 5 we have kind of very high values of magnitude, which indicates that yes, my 5 hertz and 10 hertz were my original frequency content, and remaining are low values which are appearing because of factors like windowing and spectral leakage thing. But overall we are able to get the picture that these two frequencies are present. So, this is doing what my normal DFT will do, and not only that, it is telling me that these components are present in the entirety of the signal. What about increasing the complexity of the problem? Let us say I have a signal from 1 to 5 seconds of a sine wave of 10 hertz, but from 2 to 3 the signal will display an oscillation of 30 hertz, and outside this it is 10 hertz again, like something like slow and then suddenly fast and slow, which is marking that here some event has occurred. Now, if we do the DFT as I explained, you get both the frequency content, but where this 30 hertz appeared you do not know. So, this is the piecewise representation of the signal, and this is the time domain representation of the signal. So, clearly we see that from 2 to 3 hertz this fast oscillations have happened, but although this is visible in time, it is not visible in the frequency. We just know those 30 hertz and 10 hertz are present, but in the time again we know that there is something happening here, but we clearly do not know that this is 30 or this is what frequency. So, here comes STFT to our rescue, and now we clearly see that since this yellow is representing highest magnitude, we see that in this region, say 1 second to 2 second, my 10 hertz is the dominant frequency, and then 2 to 3 I can see that 30 is the dominant frequency, which indicates that this dominant frequency has occurred in this region 2 to 3 seconds, and then afterwards again from 3 onwards we get 10 hertz as the dominant. Now, I request you to try this as an assignment, that here you keep 10 throughout and also add 30 in this region, and you will see that this yellow line is throughout, whereas this 30 hertz component represented by this yellow line is only for 2 to 3 seconds. So, I will end this with some properties of STFT. First is linearity, and just like all the previous transforms, this STFT is also linear, which means that if I do linear combination of two signals xn and yn with constants a and b, I get the product, the linear combination of the transforms in a similar way or similar weights. So, this is useful when we are given with the STFTs of say smaller signals, and we can calculate with for a larger complex signal, which is a combination of those smaller signals. Another property is the shift invariance. So, if I shift this signal in time domain by a factor k, then only the phase will be changing and the transform in the magnitude spectra or the STFT in general will be preserved. So, thank you so much. Have a nice day.